In this section, we're going to be discussing a concept that is very useful for understanding matrices and linear transformations. So to motivate the discussion, let's start off with a linear transformation from R2 to R2. Let's let T be the linear transformation induced by matrix A, which is 1, 6, 1, 0. So that means for any vector x I plug into the transformation to evaluate the transformation on x, I'm just going to multiply x on the left by matrix A. Okay? So let's understand this visually. Let me pull this over here. We're going to take this example, this illustration, this interaction from the textbook. So we have here, we're starting with several vectors in R2. Now what we want to do is we want to see how the linear transformation we just described, if we apply these vectors, what happens to these vectors? Okay, so I'm going to drag this slider, and that's going to transform these vectors into the vector we get after we apply the transformation. So here's the original vectors, and then if we apply the transformation, if we multiply each of these vectors by that matrix, 1, 6, 1, 0, this is what we get after. Okay, this is the result of the transformation on each of those vectors. Now, I want you to pay attention on some of these vectors one at a time. So let's look at the two sections of vectors in white. All right. Notice what happens if we apply the transformation. So I'll go slow so we could kind of see what the transformation is doing, where they end up. We kind of have a little animation so we could keep track of where they're going. Okay. So notice where they were going kind of more up and down. Now they've almost rotated so that they're more of a horizontal orientation, right? In other words, the vectors changed direction. Now, pay attention to the yellow and the blue vectors, all right? I'm going to apply the same transformation. Notice the vectors stayed on the same line they started on, right? They may have grown longer, they may have flipped around, but they stayed on that same line. They are after the transformation, the result we get is a scalar multiple of what we had to start with. All right, I'll do it again so you can see. Pay attention to the yellow and blue vectors. They will stay on the same lines. They will not rotate at all. Okay, they will keep in their same direction or maybe flip around. They might change length, but they will stay along that same line. Okay, turns out that this property of staying in the same direction, of just being a scalar multiple of what we had before, turns out to be an important idea. And that's what's happening here. These vectors, the vector in blue, the vector in yellow, it's just a scalar multiple of what we had to begin with. We're just changing its length, possibly flipping it around. Okay? But it's mostly staying the way it was to begin with. We give a special name to vectors that behave this way. Okay? So let's define it. Let A be an n by n matrix, so it's a square matrix. We say that a non-zero vector x is an eigenvector of matrix A if multiplying A by x has the effect of just scaling x by a scalar value for some scalar lambda. Okay, if that happens, we call x an eigenvector of the matrix. We say that lambda is an eigenvalue of A associated with eigenvector x. Okay, so a couple points here. Notice that generally this doesn't happen. Usually when we apply a transformation to a vector, most of the time the vector rotates. It doesn't just change its length or possibly flip around. It's not just a scalar multiple of what we had before. Usually the vector, after applying multiplying by a matrix after applying a linear transformation, it could be pointing a totally different direction. What this is saying is, in the special case that x is pointing the same direction along the same line, it's just a scalar multiple of what we had to begin with, we call that vector an eigenvector of the matrix. Okay? And the scalar multiple that goes with it is the eigenvalue. Notice that an eigenvector must be a non-zero vector. The reason for that is the zero vector isn't telling us anything especially useful. If I plug the zero vector in here and the zero vector in here, of course the statement would be true. Okay, a times the zero vector would equal to any scalar multiple of the zero vector, just 0 equals 0. We are interested in the case where the vector is non-zero. So an eigenvector must be a non-zero vector. Notice though we do not put the same restriction on lambda. Lambda could be any scalar including 0. Okay, so an eigenvalue can be 0, but an eigenvector cannot be the 0 vector.